So I always say there are sort of three kinds of instructions in an assembly language. ALU instructions, data processing, data movement, and then decision making. But there is kind of a fourth category of instructions, which are system instructions. These are sort of secondary ancillary instructions. In LC3 or MIPS, syscall is a really common instruction, and this is where you sort of, I don't want to write a routine to display something on the screen. I'll tell the operating system to do it for me. And RISC-V has these as well, and so let's look at those. This is the last little chunk of the instructions that we have. So we have system instructions here, where the opcode is 1110011, and these are I format. The immediate value is used to encode some information that you're going to send to the system. And so what do these look like? Well, we've got eCall, eBreak, return, and WFI. These are all 000 is the function, and then the immediate field actually contains the encoding for what this system instruction is going to be. eCall is a system call or an operating system call. We call it environment call. So this is where you want to ask the operating system for some help. eBreak does the same thing, except it triggers a breakpoint. So if you're doing debugging, eBreak will actually trigger a breakpoint trap instead of a system call trap. And remember, a trap is an interrupt that is caused by, or a system exception that is caused by a legitimate, syntactically correct instruction. Right? The software proceeds as it should, but the result is that we actually generate an exception that then goes and triggers the operating system to step in. What does the operating system do? Well, over here, we've got a table of common system calls. These are the kind of things that we can ask the operating system do in RISC-V. Now here we're getting a little bit past the standard specification for RISC-V, and this is why I've called this the RARS, common RARS syscalls. What's RARS? RARS is the RISC assembler and simulator. This is a chunk of software you can download and use, and it has become a very common implementational standard when you're learning RISC-V. It implements a bunch of stuff, and it is a very, like I say, a common way of doing things. Not every RISC-V implementation does it this way, but RARS is common enough that it's a good sort of example to use. So in the RARS syscalls, the operating system expects a number, a value in A7, which will tell the operating system which system call to run. And then A0 is usually an argument that will either store a value you send to the operating system or receive a value that you get from the operating system. For example, system call 1 is to print an integer. I put an integer in A0 and the operating system will display it on the screen for me. Whereas system call 5 is to get an integer from the user. It'll wait for a keyboard press, and then that integer will come back to you in register A0. We can print a string or read a string. This is a 0-terminated ASCII string. We can allocate memory from a heap. We can exit the program. We can print and read characters. This last one, number 50, I've included because it's kind of clever. It actually displays a yes-no dialog box in front of the assembler simulator for you. And then A0 is an address of the prompt, which again is an ASCII, 0-terminated ASCII string. These are the common syscalls that we have access to. Then we have X return. This is return from a system call or trap. And this X is actually what privilege mode we're going to return to. This is a little bit esoteric, but I'll give it to you really quickly. There are 3 or sometimes 4 typical privilege modes in RISC-V. The user mode is where you're going to spend your time. Your code is going to run there. When you ask the operating system for help, you're going to promote to supervisor mode. That makes the thing do some things that you're not allowed to do. And then when it's done, it'll return back to user mode. And so we have a special instruction called URET, right? That is going to return from supervisor mode to user mode. And the X can be either M for machine mode. This is the highest level of privilege, and it operates on the lowest level of hardware. H is for hypervisor. This is a sometimes used intermediate mode between machine and supervisor. And then S is for supervisor, and U is for user. So then WFI is a system instruction that makes the machine wait for an interrupt, which again won't be that common. And then this last one, function 3, CSRRW. This allows you to read and write control status registers. Again, we're getting a little esoteric here, but I'll just put it in for completeness. These control status registers store information about what the machine is doing, and we use the CSRRW instruction to store those registers in the register file or retrieve them from the register file. And this is a slightly faster way of doing things than pushing them on the stack if we have to change status modes for some reason. So this is, again, a little esoteric, but there may be some reasons to do that. The other service instructions we have are address construction instructions. The immediate value typically is about 12 bits. And so if you're using a branch, you got 12 bits away, plus or minus 2 kilobytes or whatever. If you want to go further than that, you may need to construct a larger 32-bit value. And we have a couple of service instructions that allow us to construct 32-bit values. Load upper immediate and add upper immediate PC both start with 20 bits, and then you can combine those with a regular 12-bit to get a 32-bit number. So load upper immediate, both of these actually are in U format. Another new format, let's look at it. U format has 20 bits of immediate value, all standard, and then the destination register, and then the opcode. And then if you look in the immediate value, it actually constructs an immediate value with those 20 bits at the top half of a register so that the last 12 bits are 0. So you can combine that with an AND instruction, an AND immediate, and then load upper immediate, and immediate, and then you get a 32-bit constant as a result. And so these are used for constructing 32-bit addresses, either in absolute with load upper immediate and then AND immediate, or relative to the program counter with add upper immediate to program counter. So these are two different variants, which basically give you the same thing. Take the immediate value, shift it up by 12, and then put it where you're going to be using it. And finally, and again for completeness, it's unlikely you'll use this, but it's in here. And when we actually start to build the machine that does this, you'll see why it's useful. We have fence instructions. Typical machines these days are made with pipelines, which means you start an instruction and then it starts to work its way through the hardware and you start the next instruction. So at any one time, there might be a few instructions executing at the same time. In fact, for RARs, we have a 5-segment pipeline: instruction fetch, instruction decode, execute, memory, and write back. If you haven't done pipelining, don't worry about any of this stuff. Fence just allows you to control that pipeline a bit. If you need one instruction to complete before you start the next one, you put a fence between them. And then that forces you to flush the pipeline before you start the next one. Two kinds, one for data. Fence 1.1 allows you to fence memory, so you have to complete memory before you start the next memory. And you can specify whether you're going to complete input or output or read or write. And then fence.I is instruction fence. You have to complete the execution of one instruction before you start the next. So those are the system instructions, the sort of extra ancillary instructions, and combined with our branches and jumps, our loads and stores, and our ALU is the complete specification for RISC-32 integer format.